In this two-part module, we're going to take a look at the potential impact of artificial intelligence on organizations with a focus on generative AI and large language models, or LLMs. In 2023, when Google publicly beta launched Bard, its counterpart to ChatGPT, the demo featured the following question: what new discoveries from the James Webb Space Telescope can I tell my 9-year-old about? Its 3-bullet point response included a factual error, namely that the telescope had taken the first pictures of an exoplanet, a planet outside our solar system. This was wrong. And it's called a hallucination in large language models, something we'll come back to. In fact, the first exoplanet, 230 light years from Earth, was photographed 19 years earlier in 2004. When news of the error went viral, Google quickly lost $100 billion in market value. AI is a high-stakes game that will drive the future of our economy, for better or for worse, especially generative AI and LLMs. AI will create and destroy jobs and force us to make difficult philosophical and ethical choices about our future. The genie is out of the bottle. Our learning goals are to provide a high-level overview of AI, or a review for those of you familiar with the technology. We'll also distinguish and discuss differences and overlaps between LLMs and generative AI. Finally, we'll hopefully stimulate some thinking about the impact and ethics of AI on the future of work. Now, let's dive into a quick taxonomy of various constructs in artificial intelligence with a focus on two key areas: large language models and, more broadly, generative AI. Both are a subset of a broader set of AI technologies we all know as machine learning. Machine learning refers to a class of AI in which data models are used to make predictions about the world with increasing accuracy. For instance, pricing that predicts purchasing behavior, or a radiologic image that predicts a cancerous tumor. Machine learning comes in two main forms: supervised learning, where data are labeled, and unsupervised learning, where data aren't labeled. For example, if you're using machine learning to train an image reader how to distinguish a cat from a dog, supervised machine learning would have each photo in the training set already tagged as a cat, dog, or neither. Unsupervised machine learning would require the system to learn to distinguish between cats and dogs on its own, though some feedback would be required for the system to learn. Deep learning is a more complex, semi-supervised version of machine learning that mimics the neural structure of the human brain and usually requires human intervention to provide feedback, enabling the model to learn, at least in the earlier stages of model training. Computer scientist and cognitive psychologist Geoffrey Hinton is a pioneer of this neural network approach to deep learning. Large language models, or LLMs, like ChatGPT and Bard, use semi-supervised deep learning trained by large data sets to generate original linguistic content. That's the distinct feature here, that can include written text or computer code. We'll see in a moment how that happens in abstract. Finally, generative AI is a broader, overlapping construct that can include LLMs, but that also goes beyond text to generate content that may include video, visual images, sounds, including voices, or even music. For instance, OpenAI's DALL-E, Google's Gemini, and Microsoft's Copilot generate visual content in response to textual instructions. Let's now turn our focus to LLMs and generative AI. As a subset of generative AI that uses deep learning algorithms, large language models rely on 4 key concepts to transform a learning data set into original content. Let's go over each concept for ChatGPT, which is an acronym for Generative Pre-trained Transformer. LLMs start with word vectors. Now, word vectors are tokens that are converted into quantitative vectors that are mapped into hyperdimensional space. Okay, let's translate that. First, words are actually broken down into smaller linguistic units called tokens. For instance, the possessive pronoun hers might be broken into 2 tokens: her, signifying a female singular pronoun, and s, signifying a possessive form. Tokens are correlated with each other through quantitative vectors. In other words, her is correlated with tokens that precede it and words that follow it. with higher frequency word associations having higher correlations. In this regard, the meaning of the tokens themselves aren't even relevant to the system, only their correlations with other tokens. Now, you can think of this as analogous to a social network map where each token is a node and the vectors are connections running through the nodes. The connections take into account context as well. We'll see this in a moment. For simplicity, we'll refer to tokens as words. Now, layers and parameters are the quantitative linkages between words that account for the context learned from the prior layer. That is, word vectors account for the context in which a word appears. This quantification happens through an attention step in which scores are calculated between the current word being evaluated and all other words in the input sequence. An attention score is calculated as a weighted sum of word vectors producing a context vector that captures information to generate the current word. Another way to think about the attention score is the probability of a sequence of words accounting for the context of each word in the sequence. Finally, the feed-forward step is where the attention score is used to predict the next word in the sequence. Once predicted, that next word becomes part of the attention step until the attention score predicts the next word in the feed-forward step, and so on. This sequence continues until the process is complete. Let's take a closer look at each of these concepts, starting with word vectors. As mentioned earlier, word vectors are analogous to social network diagrams where nodes are words with vectors connecting words based on a score that accounts for context and syntax. For instance, word associations or analogies can be accounted for. As shown in the examples, this enables the system to quantify relationships such as nationalities, capitals, opposites, plurals, or genders. For instance, man is to woman is a vector as king is to queen, and big is to biggest is a vector as small is to smallest. These vectors enable the system to quantify the context in which a word appears. Through this process, the system can convert words into mathematical expressions. As an example, based on the relationship of countries to capitals, Berlin minus Germany equals Paris minus France. Therefore, using simple algebra, this can be converted into the expression Berlin minus Germany plus France equals Paris. ChatGPT, or Generative Pre-trained Transformer, uses a transformer architecture in which word vectors are broken into layers. Each layer is a sequence of words accounting for context that's calculated by the attention score at the attention step. In this example, each layer accounts for the syntax where John is the subject and wants and to cache are verbs. The attention score calculates the probability of the next word in the sequence with the highest score selected as the feed-forward step. In this case, the word check gets the highest score and is therefore selected for the feed-forward step. Think of it like Wheel of Fortune on super steroids. The feed-forward step relies on a mind-numbing number of calculations. For ChatGPT version 3, released at the end of 2022, OpenAI estimates that it took 300 billion trillion calculations to train the large language model, using a training corpus of around 500 billion words that drew from internet data up until 2020. By comparison, a human child has encountered somewhere around 100 million words in their first 10 years of life, or about 0.02% of the size of ChatGPT-3's training dataset. The key takeaway here is the complexity of these models is absolutely beyond our comprehension.